Hello everyone and welcome to Pre-Calculus Algebra lecture number 15, I think. 15, part 1. And today we're going to be talking about polynomials. Here we go with the preliminaries. But before we can talk about polynomials, we have to talk about monomials. Mono meaning one. A monomial in the variable x is an expression of the form c x to the n. C can be any real number constant and is called the coefficient. N, that's the exponent. N can be any non-negative whole number and is called the degree of the monomial. Now, you know what? I think I better underline whole number also. The degree or the exponent n has to be a whole number and it has to be non-negative, which means that it could be zero. It could be zero. Zero is non-negative, right? So the degree n has to be a non-negative whole number. The coefficient c can be any real number constant. Any real number constant. Let's look at some examples. Our first example. All of these expressions are monomials. This one's pretty obvious. Monomial of degree 3, and the coefficient is 5. This one, the coefficient is 6, and the degree is what? The degree is 2, right? Here, this is negative, but that's okay. The coefficient can be any real number constant, including a negative constant. So coefficient is -7, and the degree, that's 4. Now what about this one? We have 3/2 out front. That's not a whole number. The constant coefficient doesn't have to be a whole number. The coefficient can be any real number. So the coefficient is 3/2, and the degree 2. Now this one, the coefficient is 4. But what about this? We're supposed to have x to a power, right? I claim that the degree is 1 And here's why I say that. Here's the defense of my answer. 4x equals 4x to the first power. This can be written as 4 times x to the first power. So the exponent, or the degree, of this monomial is 1. Hey, this one I think is a little bit more problematic. How does 2 get to be a monomial? Well, let's write our notes down here. Can we write 2 as some constant times x to the power of a non-negative whole number? What about this? X to the 0 is 1, right? So this is 2 times x to the 0. And the exponent is a non-negative whole number. So yeah, 2 is a monomial. The coefficient is 2. And the degree is 0. So what this example tells us is that any constant, any real number constant, is a monomial of degree 0, including this constant, 0. Now I can write that a lot of different ways. For example, I could say it's 0 times x to the 0. I could also say it's 0 times x to the first, can't I? And so on. But tell you what, let's just say that it's 0 x to the 0. And that way, we'll say that the coefficient is 0 and the degree is 0. And I'll tell you why I opt for saying that the degree is 0. This is a constant, and just to be consistent with all other constants, for all other constants, the degree is 0. So we'll just say that the constant 0 is a monomial of degree 0 also. 0 times x to the 0. Now let's look at another example. None of these expressions are monomials. In each case, let's see what it is that disqualifies each expression from being a monomial. First, we'll look at this one, 3x to the negative 2. What's the problem with this one? The coefficient is a real number, no problem there. So the problem must be with the exponent. And do you see the problem? The exponent is not a non-negative whole number. The exponent is negative, so it can't be a non-negative whole number. So the problem is right there. Now let's look at the next one. I could write this as 4 times x to a power. Square root of x is the same as x to the 1/2 power, right? The coefficient's fine. The problem must be with the exponent. Exponent is not what it should be. Let's see. The exponent is non-negative, so what's the problem? It's not a whole number. The exponent is not a whole number. So that's the problem. And similarly, 6 cube root of x can be written this way, 6 times x to the 1/3. But we have the same problem here that we have up here. The exponent is not a whole number. We defined what a monomial is, and that helps us to define what a polynomial is. So here we are defining polynomial. A polynomial is the sum of one or more monomials. So we just take a bunch of monomials, add them together, we got ourselves a polynomial. That's the way it works. And notice this says a polynomial is the sum of one or more monomials, which means we could have just one monomial, and the monomial is also a polynomial. This is the sum of one monomial. By the way, for those of you who are scrutinizing what I say, when I talk about sum here, I'm talking about a sum having finitely many terms. To most of us, that's not going to be a concern, but just to make sure I say this absolutely correctly. A polynomial is the sum of one or more monomials, and when we say sum, we're talking about finitely many terms. All of the expressions below are polynomials, and two of them are actually monomials. This is a monomial, that's a monomial. So not only is every constant a monomial, every constant is also a polynomial as well. Here we have the sum of 4 monomials, and the term having the highest degree is this one. This term has degree 4, so that's also the degree of this entire polynomial. This polynomial has degree 4. This is a monomial, also a polynomial. It has degree 3, so this polynomial has degree 3. This is a constant, and every constant is a monomial of degree 0. We can write 5 as 5 times x to the 0. So this is a polynomial of degree 0. And remember, we agreed for the sake of being consistent that every constant is a monomial of degree 0. Here's a polynomial. It has 1, 2, 3, 4 terms. And the term of highest degree is this one. The degree of this term is 4. So that's the degree of the polynomial as well. This polynomial has degree 4. Let's consider a definition here because it mentions specifically the way in which polynomials are written. This is a universally agreed upon convention. It says a polynomial is in standard form exactly when two things happen. First, the term of highest degree is the leftmost term. And secondly, all terms appear in descending order according to degree as we go from left to right. And actually, criterion number 2 does define polynomial completely. If a polynomial is in standard form, the term of highest degree will be the leftmost term. In this case, we have degree 4, degree 2, degree 1, degree 0. The term of highest degree, degree 4, is the leftmost term. So let's make a few notes about this. This is in standard form. The leading term is the leftmost term, the term of highest degree. So we'll say leading term is 9x to the 4th. And I think I might want to add something here in a minute, so I won't close the parentheses over here. Let's look at this polynomial. Degree 6, degree 4, degree 2, degree 0. The term of highest degree, degree 6, is the leftmost term. So this is in standard form. The leftmost term is the term of highest degree, and the terms appear in descending order according to degree. Degree 6, degree 4, degree 2, degree 0. So this is also in standard form. The leading term is negative 8x to the 6th. And what about this one? X to the 4th, degree 4, degree 9, oops, not in standard form. Maybe we can rewrite this. Take the term of highest degree and put it first, and then add the rest of the terms going from higher degree, x to the 4th, to lowest degree. I think we have it. degree 9, degree 4, degree 3, degree 0. We've got it. So now I can say that it is in standard form. And I can say the leading term is the leftmost term, which is 6x to the 9th. Now there's something else that I might want to mention here. Sometimes we talk about a leading coefficient, and a leading coefficient is just the coefficient of the leading term. Here's the leading term, 9x to the 4th. So the leading coefficient would be the coefficient of that leading term. What about this one? Here's the leading term, and the constant coefficient of that term is -8. So -8 is the leading coefficient. This guy, it's not in standard form. I can close the parentheses on that one. On the line below, I took this polynomial and rewrote it in standard form. So this is the leading term, 6x to the 9th, and the leading coefficient is 6. Bravo. You know, since I have all of these up here, I probably should introduce one other piece of terminology. Each one of these has a constant term. Not all polynomials do. But the term of degree 0, if there is one, is the constant term. In this first polynomial, the term 1 is the constant term. In this second polynomial, the term -8 is the constant term. And in this thing, the constant term is 1. Now that leaves us to figure out one oddball situation. Can you think about what it is? There's a pathological case that we haven't considered, so let's consider it now. Let's look at this polynomial and notice that the terms are of degree 6, degree 4, degree 2, degree 1. So the term of highest degree is the leftmost term, and the terms appear in order of their degree in descending order, degree 6, degree 4, degree 2, degree 1. The terms appear in descending order according to degree as we go from left to right. So the degree is 6. The leading coefficient is the coefficient of the leading term, or the leftmost term, which is 8. And the constant term is, there's the problem. We don't see a constant here, do we? There is no constant term. Or maybe there is, but we just don't show it because that constant term is 0. Did I just change this polynomial at all by adding 0? No. We can add 0 to any real number expression, and we don't change its value. So if no constant term appears, there really is a constant term, but we just don't show it because typically when we add 0 to an expression, we don't change the value of the expression. And so we just don't write the 0 term. But the constant term is 0 in this case. So that's what happens when we don't see a term of degree 0. For a few minutes, we're going to talk about what a power function is. A power function of degree n is a function of the form f of x equals a times x to the n. Okay, a power function is a monomial of degree n. That's what a power function is. Ooh. So why do we care? Why do we care what a power function is? It's just a polynomial of degree n. Well, it turns out that polynomials of degree n and power functions of degree n have certain characteristics in common. And if we know what the graph of a power function of degree n looks like, then that also tells us quite a bit about what the graph of a polynomial of degree n will look like. The graphs are going to have certain important things in common. And what's true of a power function of degree n is going to be true in several respects of a polynomial of degree n. So we're going to take a brief look at power functions. First, let's look at power functions of even degree. And we'll consider the graph of f of x equals x to the n, where n is an even number, 2, 4, 6, 8. And what does the graph look like? Well, let's not forget our old friends, -1, 0, and +1. When x is -1, -1 to the power of an even number, for example, -1 squared, is going to be +1. So the point -1, +1 is a point on the graph. When x is 0, 0 to the n power is 0, so 0, 0 is a point on the graph. And when x is 1, 1 to the nth power is 1. So 1, 1 is a point on the graph. And our power function for n even looks like this. And let's consider just a slight variation of this. F of x equals ax to the n, where a is positive and n is even. So we have x squared, x to the fourth, x to the sixth, and so on. The shape of the graph and its orientation are going to look very much the same. Realize what this is. This is a vertical stretching by a factor of a. So in the original graph, the y coordinates all get stretched by a factor of a. A times 1 is a. So negative 1a is a point on the graph. 0 gets stretched by a factor of a, but 0 times a is 0. So 0, 0 is a point on the graph. And when x is 1 and y is 1, the y factor, or the y component of this point, gets stretched by a factor of a. We multiply the y coordinate by a, and we get the point 1 positive a. And there is the graph of the power function f of x equals ax to the n. See that? Don't forget our old friends, negative 1, 0, and positive 1. Now let's look at power functions of odd degree. X, or x to the first. X cubed, x to the fifth. Let's see what these things look like. And we look at our old friends, x equal negative 1, x equals 0, x equal positive 1. When x is negative 1 to an odd power is negative 1. So the point negative 1 is a point on the graph. When x is 0, 0 raised to the n power is 0, so the point 0, 0 is on the graph. And when x equals 1, 1 to the n power is 1. The point 1, 1 is on this graph. And this is what x to the n looks like in general. We'll make a slight exception if f of x equals x, or f of x equals x to the first. In this case, the graph does go through these points, but the graph of f of x equals x, this is the graph of a line, or the equation of a line, isn't it? So if f of x equals x, our graph is going to look like this. It still goes through the key points, but f of x equals x is the equation of a line. Now we're going to modify this slightly. F of x equals ax to the n, where a is positive. So all this does is stretch things out vertically. That we take the y coordinate of each point on the original graph and stretch it by a factor of a. We take the y coordinate, measure it. You know what? This is not right. When x is negative 1, x to the negative 1 is negative 1. I apologize. I was missing a minus sign here. To get the graph of f of x equals ax to the n, we multiply the y coordinate by a. So a times -1 is -a. To get the corresponding point, or the point that corresponds to this point on the new graph, we take the y coordinate and multiply it by a. 0 times a is 0. So 0, 0 is a point on this graph also. And then to get the point on the new graph that corresponds to this point, we multiply the y coordinate by a. A times 1 is a. And that gives us the point 1a. And here is our graph. And this is what f of x equals ax to the n looks like when a is 0 and the exponent is odd. Now we'll have to modify this slightly if the exponent is 1. If the exponent is 1, the graph is f of x equals ax. That's the graph of a line. And so that's going to have a graph that looks like this. But this is what the graphs of our power functions look like. And we're interested in what the power functions of degree n look like because their graphs have certain things in common with the graphs of polynomials of degree n. And the graphs of the power functions will tell us something about the graphs of the corresponding polynomials.